Now we can implement the causal self-attention. Like we discussed in the theory, this allows tokens to actually talk to each other now. We will see how this is being implemented. We will start with another class. We'll call it causal self-attention, and is going to inherit from an index module, just like the previous MLP class. And then we will define the constructor for this class, and it's going to take self and config exactly as before. And inside of here, first thing we're going to do is pass this. Let me fix my spacing here. And yeah, we will first define a linear layer. Or actually, before that, we need to assert something very important, like we discussed in the theory. We're going to divide the dimensionality for each token by the number of heads that we have, which is 12 here. So if we were to do that, 768 divided by 12 is going to be 64, and that's how many feature or how many variables about each token each attention head is going to control. So we need to assert that if we were to define config and embed, if we to divide this by config dot essentially the number of heads, we should be able to get exactly 0. So this assertion is very crucial, like we discussed, because otherwise we're not guaranteed to have the same number of features for each head. After we asserted that, let's go ahead and define our first layer, which is going to be self dot, we're going to call it C attention, and it's going to be another linear layer. And the inputs of that is going to be config dot nembed, and the output is going to be config dot nembed, except is going to be multiplied by 3. And the reason should be straightforward, because like we discussed in the theory, we need to expand this by 3 to allow each token to embed more information about the key, the query, and the value, which will help it to communicate with other tokens. So after we define this layer, we're going to define another layer. We're going to call it self.cproj. And this one is going to be another linear with config.nembed and config.nembed. Essentially what this does is it preserves the dimensionality after we expand it or project it to the same output. And so after this, let's go ahead and store some information here from the config through our nembed or the head first. So we're gonna grab this from the config.nhead. And also let's do the same for the embeddings. So nembed equals config.nembed, because we will use that in the forward. So yeah, now let's define our forward function. So we're going to say def forward. It's going to take self and an x, which is our input. And first of all, let's define 3 things that we're going to extract out of that x. These are b, t, and c. And these are going to be equal to x dot size. So what we're doing here is extracting the batch dimension, the t dimension, and the c. These are these numbers here, essentially. So our batch size is how long our batch is, which we haven't defined yet, but we will do during training. But t is the 1024, which is the length of the sequence, the context window. And c, again, is the dimensionality for each token, which is 768. Now, after we get that, let's go ahead and do a kqv new variable, which is short for q, key, and value. And these are going to be equal to the output of our of passing our input through the first layer here. And this is combined, so this is all values together. So we need to get them more explicitly. So qk and v are going to be equal to that previous value dot split self.nembed and dimensionality equals to, or the dimension rather is the third dimension because it starts from 0. So remember this layer here. What it does is it scales our input dimensionality by 3. So the shape of this is going to be b, t, and c times 3. So we want now to obtain values for the query, key, and value for each token, which is going to be divided, or we're going to split that across the third dimension here. So it's going to split that to get these values explicitly. Now for each of these values, let's start with q, the query. Is going to be equal to query.view. We're going to view this in the format of b, t, self.nhead, and c integer division by self.nhead. And then we're going to transpose that, and we're going to repeat that 3 times for the K and for the V. The next step is to actually apply the dot product between these and calculate the attention like we saw in the theory. So we will call the output Y, and that's going to be f dot scaled dot product attention, and the inputs for that is going to be the query, the key, and the V, and very importantly is causal, which is going to be equal to true. So what this does is actually compute the matrix multiplication and give us the value for the attention, or apply the attention between all the tokens and compute the attention matrix. And because we're passing this is to true, is going to be in a causal fashion, meaning that attention for that token is based only on the previous tokens that came in the series and not on future tokens. And after we did that, let's do a transpose. So transpose the Y and essentially combine the inputs into one vector, because remember we did the splitting here, so now we're going to combine them up. So contiguous, I hope I'm spelling this right, Q, K, and V contiguous, I hope I'm spelling this right. Then this is going to be dot view into our desired shape, which is B, T, and C, which is what we started with over here. And yeah, after that we're going to apply our last layer here, which is self.cproj, and we're going to give it our Y, and of course we're going to return this as the final output for our self-attention. And this allows us to obtain 3 different variables, the query, key, and value for each token. And then we obtain these explicitly. We applied the dot product between them, essentially allowing them to talk to each other, and this is the core of the whole causal self-attention, and we're doing it in a causal way, essentially preventing communication from the future. Only sequences in the bag are allowed to communicate or influence our current prediction. And then we applied our final projection to maintain our nice and clean BTC shapes.